In this video, we're going to show you how to compare two population proportions if we take a sample from each of the two populations. So let's get started. In this example, we have a random sample that we have taken in city 1. And after we take the sample, we ask the respondent whether their household own a cat or not. If they own a cat, we would denote their results as Y, otherwise would be an N. We do the same thing for the random sample that we take from city 2. And we wish to use these two samples to test whether the proportion of households owning a cat is different in the two cities. So if you scroll down and look at the data, we have about 186 data points, the sample size for city 1, and we have exactly 200 for city 2. So what we can do is we first want to summarize that data, and one way of summarizing the data is by way of, first of all, the sample size. So we can either count the sample size or we just put it there. So let's just count them. So we say count A2 to A87. And so that would be 186. And if you want to make sure this is right, then this is there. And we also want to calculate the sample size for sample 2, which is obviously either we just put 200 or we can actually do the same thing as count A, B2 to B201. All right. So that's the population, that's the sample 1. That's sample 2. And then now what we need to do is we need to calculate, or we need to summarize the two samples in terms of how many Y's are there. Right? So number of Y's, number of yes. And to do that, we can use Excel function countIF. So we say countIF A2 to A187, and we're interested in counting yes. And sorry, the reason why we have 0 is because we only put Y there, right? And so there's 70 of them in sample 1, and see what we have in sample 2. We do count if B2 to B201, and again we count yes. All right, so now that we know the sample size and the number of yeses, then we can now estimate the proportion for each of the two samples. Right, to do so, we just take this number, divide by this number. So we are calculating the sample proportion. Sample proportion, we also use PBar to denote it in many texts. So let's just make sure that we have a little bit more space to do that. Right. So how do we do that? Well, we take E6 divided by E5. And we're going to express this in terms of decimal point. So that's why it's called proportion. And we can now copy the same formula and calculate the same thing for sample 2. And we would like to compare the proportions based on the sample proportion that we have obtained. So let's just write down what the parameters are. So we have P1. P1 is proportion of households owning a cat, and P2 is same thing. Let me just make sure that we have specifics in city 1, and this is let me just copy this, and P2 is just the same thing, except this is for city 2. And what we want to do based on the research objective is that we want to compare the two proportions and see where they are the same. So let's go through the 5-step process. The first step, of course, is the hypothesis. So we write down the hypothesis, HA first. HA is P1 is not equal to P2. And this is obviously a two-tailed test or two-sided test. And HA, of course, H0, of course, is that P1 is equal to P2. Now, in order for us to do this test, we need to go through a number of things in order to get at the test statistics, and then we can calculate the p-value or the critical value. So let's just use the p-value approach first. So let's define alpha to be, say, 0.05. And under the p-value approach, we say reject x0 if the p-value is less than 0.05. Okay, and the good thing about the p-value approach, as I said, is one is universal. It doesn't matter what problem you're doing is the same rejection rule. The other thing is that we can, once the p-value is calculated, we can actually judge quite easily how significant the results are. It's actually without the reference to the alpha level. Now, the meat of the whole process is the calculation of the test statistic as well as the p-value. In order for us to calculate test statistic, we have to go through the first step process. The first step is to calculate the p-bar. Now, p-bar is what we call the poor proportion. The concept is that under the null hypothesis, so if the null hypothesis is true, even though that we take a sample from city 1, a sample from city 2, these two samples could be considered to be from the same population because P1 is equal to P2. So as far as the proportion of household owning a cat is concerned, we can treat city 1 and city 2 as the same population. And therefore, we can estimate the overall proportion based on the combined sample if the null hypothesis is true. So we can either go through this calculation, or if you want to, you can just combine the two samples and come up with the combined population. And that most of the time is probably easier, right? So we calculate p-bar. P-bar is equal to, either we use the formula here, so it's N1 is 186 times P1 is 0.376, and notice that if you do that, you would have a slight rounding error because we actually round these two numbers up, right? And then obviously N2 is 200 times 0.420. So that's and then you divide by the combined sample size, which is 186 plus 200, right? Or as I said, right, the easy way of doing it is you say, okay, under the null hypothesis, we can combine the sample. So the combined proportion will be 70 plus 84 at the top, right? So this is the combined number of households that own a cat. And then the bottom, of course, is the combined sample size, which is 186 plus 200. And as a good practice, we always round them to 3 decimal places. And so therefore, if you do that, it will be 0.399. And as I said, if you use this formula, you may have a slightly computational error because of the rounding, due to rounding, right? Because we round these numbers to only 3 decimal places and this number to only 3 decimal places. Now, so once the combined proportion is calculated using this formula, or combine the two samples into one, either way is the same thing, then we can calculate the test statistics, right? The test statistic is very much the same as what we see in the past, right? You compare what you see from the sample. What you see from the sample is the sample proportion for the first population and the sample proportion from the second population, and you compare them. Without statistical training, you would say, oh, that's it, right? That's the difference. with statistical training, you know that you have to take into account the variability of the data, and this is how you take into account. And this is the kind of a variance calculation for the combined proportion, right? So it's rather complicated if you do it by hand, but it's actually very much doable. So the test statistics, if I write this out, would be 0.376 minus 0.420, right? That's the comparison of the two sample proportion divided by square root of, and the bottom is the combined proportion, which is 0.399 times bracket 1 minus 0.399, and then times 1 over N1. N1 is 186 plus 1 over N2, which is 1 over 200. And that's the formula that you would need to put together. And let's just copy this, and then we can just calculate this in Excel, and then we would get a number, and that number would be our, right, so this is 0.8821. That's our test statistics. Now, at this point in time, you can calculate the p-value. The p-value is, first of all, is the area of the tail that go beyond the test statistics. So in this case, because this is on the lower side, negative actually 0.88121 is about here, right? So we calculate the tail area. This is 0.8821. If we calculate the tail area, but then because of the fact that this is a two-tail test, we have to take the result and multiply by 2. Okay, so the p-value is equal to 2 times the probability of Z is less than negative 0.88. Right, so if you're using a table, then that's it. If you're using Excel, you can actually keep the 4 decimal places if you want to. In this case, it won't make much of a difference. So if you use Excel function to calculate that, this would be 2 times norm.dist and 0.8821, right? And mean is 0, standard deviation is equal to 1, and then it's true, and that would be it, right? Now this is very important. You know, if you want to make sure that you're doing the p-value calculation the right way, you should always draw a picture. If in case that this is a upper tail situation, then you know, oh, if I want to calculate upper tail, I need to calculate the lower tail and then 1 minus that, right? And to ensure that you would do that properly every time, drawing a picture would help you in visualizing what you need to do. All right, so now let's just calculate this. So the p-value is 0.3777, and obviously that number is not less than 0.05, so we do not reject. Also, you know that it doesn't matter what alpha level is, the result is not significant. So you can look at this number and say, well, based on the data that we've seen, there is actually not much of a difference in terms of proportion of households owning a cat in these 2 cities, right? So we say since the p-value equal to 0.3777, which is not less than 0.05, so do not reject, and so therefore we have insufficient evidence to conclude that the proportion of households owning a cat in these 2 cities is different. Okay, so that's how you do it. It's actually pretty straightforward. Once you realize that this is the way that you calculate the test statistics, then you can utilize whatever we learned in the past to do them. Let's just do the same problem, except that we're going to use the critical weight approach and see whether there's any difference that we need to pay attention to. All right, so let's just, the first step, of course, is the same. So if you're using the critical weight approach, right, the parameter definition is the same. The hypothesis, of course, is exactly the same. Alpha is the same, right? So the rejection rule is different because it is because of the fact that we are using critical value. Let me just put this aside for now. And what we need to do is to find the critical value for two sides, right? Because why? Because this is a two-tailed test. So we need to actually find the critical value on both tail. All right, so we need to do that. Now, so how do we find this value? Well, alpha is equal to 0.05. So together, the two tail together is 0.05. So one side is 0.025, and we need to find a number here so that the area in the normal distribution is 0.025. So we want to find A such that probability of Z less than A is 0.025, right? So how do we do that? Well, all you have to do is use the INV function. So critical value is equal to, right, norm dot INV, right, 0.025, 0 and 1, and that would be something that you can actually calculate, right? Or you can use the table. Either way would be fine, right? So let's just calculate this norm dot INV 0.025, and if you remember, that number should be negative 1.96, and so therefore this is negative 1.96, and therefore this number is positive 1.96. So our rejection region would be reject x0 if Z is less than negative 1.96, right? Because this is a two-tail test, so we have rejection region on both tail, or Z is greater than 1.96. Okay, so that's how you set up the rejection rule. Again, it's so much easier if you actually draw a picture and you can actually see what's going on with what you need to do. All right. So step number 4, of course, is exactly the same. So we can just copy down, right? We still calculate the same, actually same two-step process. You calculate PBar first, the combined proportion, and then you calculate Z, which is the test statistics. Except this time, of course, you do not have to calculate the p-value. You can use the rejection rule to reject, right? So where is negative 0.8821? Negative 0.8821 is around here. 0.821 is around here. And so negative 0.8821 is not in the rejection region. So we do not reject, right? So we say since Z is equal to negative 0.8821 is bigger than negative 1.96 and less than 1.96. So we do not reject x0, and so we have the same conclusion that we have before. Okay, so that's how you perform the same test using the critical value approach. And notice that the approach that we're using is exactly the same as before, right? So the logic that we established is exactly the same. The only difference is that we are using this particular test for us to test the equality of two population proportions. The last thing we want to do, of course, is to see In some cases, we want to do a confidence interval for the difference between the two proportions. We can actually do that, right? So let me just write this down for you. So a 95% confidence interval for the difference, right? So this one is the difference of the population proportions. That means P1 minus P2 would be the following. Now, it actually doesn't matter whether you're doing P1 minus P2 or P2 minus P1. If you're doing the confidence interval for the difference of P1 minus P2, then you will use P1 hat minus P2 hat. If you're doing the proportion for P2 minus P1, then you would do P2 hat minus P1 hat, right? And it would be, the result should be more or less the same. One is on negative positive, the other one is positive negative. So the confidence interval would be exactly the same as you would find. All right, so so let's just use this opportunity again. If you just copy the graph here, and then we would just do the same thing, right? Because we remember that if we want to be effective in terms of finding out what we need, it's very important for us to just draw a graph. Let me just make sure that this is center back, so so we can actually put it there, right? So how do you determine Z alpha over 2 is the key, right? Because if you look at the formula, you have P1 hat, which we know, P2 hat, which we know, N1 is the sample size, N2 is the sample size. So we know everything except Z alpha over 2. So the key is to decide what Z alpha over 2 is. So the process of deciding what alpha over 2 is exactly the same as before, but let's just go through them again. So if alpha is 95%, so 95% confidence interval, so the middle is 95%. The outside is 5%, so one side is 2.5%, right? So this is the confidence interval critical value is exactly the same as a two-sided test critical value, right? So 95% in the middle, 5% outside, 2.5% one side, right? So as we already calculated, this is negative 1.96, and this is 1.96. So the value that we're going to use here is 1.96. So let's just go back and remember what P1 bar is. P1 bar is 0.376. So P1 bar is 0.376, and P2 bar is 0.420, right? N1 is 186, and N2 is 200, right? So we basically take the data that we have. This is N1, this is N2, this is P1 bar, and this is P2 bar, and we now have everything that we need. And Z alpha, Z is equal to the critical value is equal to 1.96, as we just talked about, right? So now we can actually do this, right? So 0.376 minus 0.420 plus or minus 1.96 times the square root of 0.376 times 1 minus 0.376 divided by 186. That's the first term. We want to make sure that we have all the brackets done properly, and if you really want to be careful, you can actually bracket this one as well. And then the next one, of course, is bracket 0.420 times bracket 1 minus 0.42 divided by 200 bracket, and that would be the confidence interval, right? So if you want to calculate this, of course, this is equal to 2444. So the negative 0.44 plus or minus right? Whatever the number is, we don't know what that number is, so let's just let me just calculate this number first so that we will know what that is. So we will just do it here. This is 0.0976, right? And so therefore, the converse interval is negative 0.44 plus or minus 0.0976. And the reason why the confidence interval is the reason why the confidence interval is so large, the length is so long, is because of the fact that the sample size in the context of inference on population proportion is relatively small, right? So 186, 200 is a small sample size when you try to make inference on proportions, and therefore the number are relatively small. So this is what we need to know. I hope that you enjoy the video, and I hope that we will see you soon. Bye for now.